students, in this session we will discuss about steady state AC analysis. In the previous sessions we have discussed about how to solve different circuits by using mesh analysis and node analysis. In this we will discuss about the mesh analysis and node analysis, but it is used for solving the network or circuits that containing AC sources. Up to this point we have studied about network containing sources such as DC sources. Okay. So here in the case of steady state analysis, and here we are using the sine wave as input, that is AC current as input, and here the input signal will change its polarity at different times, and here the techniques used is the same. We will use KCL rules for solving the network, and but instead of using resistance, capacitance, inductance value, we will go for impedance values, because we are analyzing the circuit with by giving the input AC. So we are using impedances in this case, or admittance. Other terms are similar, so we can start the analysis by using mesh analysis in the case of AC circuits. And in the case of AC circuit, voltage and currents in AC circuits change polarity at regular intervals. We know that if we are considering a sine wave as the voltage, and its polarity will be changing periodically. And here also it is given that V1 is input signal, and various elements in the circuit are represented by Z1, Z2 and Z3. In the previous cases we are using R1, R2, etc. and here we are using impedances Z1, Z2, Z3. That means sometimes the circuit may contain resistors, inductors and capacitors. So in that case we are using the term impedance. So, and first of all, if we are using mesh analysis, we know that we have to mark the mesh currents, and here the mesh currents are I1 and I2. So it is marked, and what is the next step? Then we will apply Kirchhoff's voltage law in the first mesh, and then again we will write the equations by using Kirchhoff's voltage law, and we will consider the second mesh and we will write the Kirchhoff's voltage law equation. So by applying Kirchhoff's voltage law to each loop, first one we are considering the first loop, we know that how can we write the equations? Starting from V1 we can write the equation as V1 minus Z1 into I1 minus I1 minus I2 into Z2 equal to 0. That is the first equation. Okay. So we can rearrange the equation as I1 into Z1 plus I1 minus I2 into Z2 equal to V1. I have written the rearranged equation. You know how to apply KVL. Starting from the point V1, the current moves through Z1 and then through Z2, and then it comes to V1. Okay, that is the current direction is in the clockwise direction. So starting from V1 we can write the loop equation. That means KVL states that algebraic sum of voltages will be equal to 0. So we can write the equation like this: V1 minus I1 into Z1 minus I1 minus I2 into Z2 equal to 0. You know that through this Z1, the currents flowing through Z1 are I1 minus I2, because I1 is flowing downwards and I2 is the other mesh current that is also flowing through Z2, and that is in the upward direction. So the net current through the Z2 is I1 minus I2. So we can rearrange the equation as I1 Z1 plus I1 minus I2 into Z2 equal to V1. And if we are considering the second loop, similarly we can write the second loop equation as Z2 into I2 minus I1 plus Z3 into I2 equal to 0. Here through the Z2 the current flowing are I2 minus I1. We are taking I2 as greater because we are considering the second mesh. So we are taking I2 will be greater than I1. That is why we are taking I2 minus I1 into Z2 as the voltage drop across Z2, and the next term is Z3 into I2, and the sum of these two voltage drops will be equal to 0. These are the two equations, and we can rearrange the above equation because in those equations the unknowns are I1 and I2. So in terms of I1 and I2 we can write the equation as I1 into Z1 plus Z2 minus I2 into Z2 equal to V1. That is first equation. And next is I1 into Z2 plus I2 into Z2 plus Z3 is equal to 0. That is second equation. These are the two equations that contain two unknowns, that is I1 and I2. We can solve for the equation. Either we can use Cramer's rule or we can use direct cancellation. So we will get the value for I1 and I2, and we can next to go to a problem, so you will get the complete idea about this. So it is same procedure, it uses the same procedure as that of the mesh analysis. Only difference is that here we are using the AC sources, so that the behavior of each component will be different. In the previous cases, we consider the sources are DC sources. We are using DC current source and DC voltage source. Here we are using AC sources. That means AC voltage source and AC current sources are using. So we will use the term impedances in that case. In the previous case, we are using resistors, and here we are using impedances. That is why it is represented by Z1, Z2 and Z3. So we can do first problem. The question is, write the mesh current equations in the circuit shown in the figure and determine the currents. Here the circuit is given. In that, the source voltage sinusoidal function, that is 5 angle 0 degree. It is its voltage value, and there is an inductor and its inductance value is J4 ohm, and there is a resistor 6 ohm, and there is another inductance its value is J3 ohm. There is another resistance 2 ohm, and I1 and I2 are the mesh currents. You can see what is this representing 5 angle 0. You might have studied it. 5 angle 0 is the polar representation, right? See, R angle theta is the polar representation of R into sin theta plus R into J, R into cos theta plus R into J sin theta. See, R angle theta can be written in the form R cos theta plus RJ sin theta. You might have studied it. And this is 5 angle 0 is a polar representation, and here inductance is represented by the value J4 ohm. You know that inductance value is J4 ohm. There will be an imaginary part in the case of AC. If you are considering the AC analysis, there will be imaginary part. If you are using capacitance, similarly we will use a minus J symbol, okay? And here this circuit contains inductors and resistors. And first of all, and we are asked to write the mesh current equations. So here the currents are marked as I1 and I2, and for the first mesh or first loop, we can apply KVL. In the KVL rule, starting from 5 angle 0, we can write 5 angle 0, that is the voltage value, minus I1 into J4 ohm minus I1 minus I2 into 6 equal to 0. That is the first KVL equation. In that equation, 5 angle 0 can be taken right into right side. So we will get 4j into I1 plus I1 minus I2 into 6 equal to 5 angle 0. In that case, we can separate I1 and I2 terms. So we will get I1 into 6 plus 4j minus 6 into I2 equal to 5 angle 0. That is the first equation. Similarly, we can write the equation for second loop. That is by applying KVL. And so we will get starting from 6 ohm, we will get 6 into I2 minus I1 plus 3j into I2 plus 2 into I2 will be equal to 0. And here we can separate I1 and I2 terms. So we will get a minus 6 I1 plus 8 plus 3j into I2 equal to 0. So we got two equations containing two unknowns. We can write those two equations 1 and 2, and this is shown here. Equation 1 is I1 into 6 plus 4j minus 6 I2 equal to 5 angle 0, and second equation is minus 6 I1 plus 8 plus 3j into I2 equal to 0. That is the second equation. So we have to solve this equation in order to get I1 value and I2 value. You can see that equation 2 gives that we can write as by rearranging the terms 6 I1 will be equal to 8 plus 3j into I2, right? 6 I1 goes to right side, so we will get 6 I1 will be equal to 8 plus 3j into I2. I1 will be equal to 8 plus 3j divided by 6 into I2. So I1 can be written in terms of I2. So we can substitute, this is equation number 3, and we can substitute this equation number 3 in equation number 1, so that we can eliminate one unknown variable I1. So if we are substituting equation 3 in equation 1, we will get I1, instead of I1 what we are doing, we are substituting 8 plus 3j by 6 into I2 there, okay. So we can write 8 plus 3j divided by 6 into 6 plus 4j into I2 minus 6I2 equal to 5 angle 0. So that is equation number 1, okay. Equation number 1 will change like this. So in this I2 term, there is only I2 terms, I1 terms are not there. So I2 can be taken outside. So rest of the terms will be like this, that is 8 plus 3j into 6 plus 4j divided by 6 minus 6 into 5 angle 0. And here you can see that some of the terms are in geometric representation and some are rectangular representation and some others are in polar representation, okay. So you can multiply these two terms, 8 plus 3j and 6 plus 4j. So you will get the multiplication terms like this, that is 48 plus 18j plus 32j plus minus 12 divided by 6 minus 6 equal to 5 angle 0. So you will get this value I2 into 36 plus 50j divided by 6 minus 6 equal to 5 angle 0. Again you can divide the terms by 6. So you will get 6 plus 8.32j minus 6 equal to 5 angle 0. So I2 into, finally you got I2 into 8.32j equal to 5 angle 0. So here one is in the rectangular form and other is in the polar form. First of all you have to convert both in the same representation. Here I am converting 8.32j in the polar form as you know that we can write 8.32j as 8.32 angle 90 degree, right? You might have studied it in the previous classes, that is 8.32j will be equal to 8.32 angle 90 degree. So I2 will be equal to, we can take this term 8.32 term to the right side. So you will get I2 will be equal to 5 angle 0 divided by 8.32 angle 90, and this can be solved like 5 can be divided by 8.32 and 0 degree and 90 degree angles are subtracted, so that you will get 0.6 angle minus 90. You should know the methods how to solve polar forms and how to solve rectangular forms, then only you can do this problem, okay. I am not going to the details of the solution of that polar forms and rectangular forms that you might have studied in the first year classes, okay. So 5 angle 0 divided by 8.32 angle 90 degree can be written as 0.6 angle minus 90 degree. You can simply substitute in the calculator and you can find the answer. Then it will be easier. Actually I am not doing that. I am simply dividing 5 divided by 8.32, so I got 0.6 and 0 degree is here the symbol is divided by, so 0 degree is subtracted, 90 degree subtracted from 0 degree, so I got minus 90. So I got the value of I2. Then I can substitute I2 value in I1. We have the equation for I1 as I1 is equal to 8.3j divided by 6 into I2, that is from equation number 3. So in that I can substitute the value of I2. So I will get the value of I1. So I1 equal to 8.3j divided by 6 into I2. Substitute the value of I2 as 0.6 angle minus 90 degree. So I got the I1 value as 8.54 angle 20.5 degree divided by 6 into 0.6 angle minus 90 degree. Actually here one is in the rectangular form and other is in the polar form. In order to solve the equation, we have to convert every terms in the same form. Here I am converting 8 plus 3j in the polar form as 8.54 angle 20.5 degree, and here I am doing that 8 plus 3j can be converted like this. I can take the magnitudes of 8 plus 3j. So I got the magnitude term, that is square root 8 square plus 3 square will be equal to 8.54. So I got the magnitude of polar form, that is 8.54. And in order to get the angle term, I have substituted the formula as theta is equal to tan inverse of 3 divided by 8. So I got 20.5 degree. You can simply do it with your calculator. In that polar rectangular to polar conversion and polar to rectangular conversion facility is available. So you can substitute in the calculator and you will get the values. So I think you might have known about that. So you can use it easily so that you can save the time. So I1 will be equal to 8.54 angle 20.5 degree divided by 6 into 0.6 angle minus 90 degree. Again it can be solved like this. Here we can multiply. We can here first of all we have to divide 8.54 by 6. That will give the I1 value as 0.854 angle minus 69.5 degree. How you got this value? 6 and 0.6 can be cancelled out, so you get a 0.1 there, and that 0.1 is multiplied with 8.54, so you get 0.854, and 20.5 degree and angle minus 90 degree is added, so you got 20.5 plus minus 90 degree, that will be giving minus 69.5 degree. So the angle terms, if there is a division process, then angle terms are subtracted. If there is a multiplication process, then angle terms will be added. Okay, that is the thing in the case of polar form. So I2 will be equal to 0.6 angle minus 90 degree, and the calculations I have given on the right side as a rough work. You can go through that. So you got I1 value and I2 value. So first of all, what you have to remember is that in this case, when we are using mesh analysis, the procedure of applying KVL rules and procedure for writing mesh equation, procedure for writing the equations for each mesh is same. But the only difference is that here the elements or branch elements are different. Here we are using inductors, so corresponding to inductance we are writing its inductive reactance in terms of J. And if we are using here, if we are using capacitor, we have to write a corresponding reactance. So here we are considering, in the case of AC analysis, we are considering impedances. Okay, that is the thing you have to remember it. Okay, so we have to sometimes use a polar representation or rectangular representation, and you can simply solve the problem. Okay, that's all about mesh analysis. Next we will go to the node analysis, and here it is given a circuit that consider a circuit that is shown in the figure, and here the circuit contains impedances Z1, Z2, Z3, Z4 and Z5, Z6, and the sources are AC source, and here the source is represented by B1. And if you are going for nodal analysis, first of all you have to mark the nodes. Here the nodes are marked as A, B and C. C is the reference node, and VA is the voltage at the node A, VB is the voltage at the node B, and C is the reference node, so the reference voltage will be equal to 0. So if you are going for nodal analysis, you have to apply Kirchhoff's current law, and for that you have to consider each node separately. First of all you go for the node A, and then you will go for the node B, and if you are going for the node A, first of all you have to mark the current directions, and you assume that all the branch currents are going out of that node. Similarly in the case of B also, you are assuming that all the currents are leaving that node. So you can write the Kirchhoff's current law equations, and so first starting with the node A, you can write here the node A, all the branches connected to node A is shown in the figure, and in that current directions are marked as I1, I2 and I3. You can see here I1, I2 and I3 are marked, and we are assuming that all the currents are leaving that node. So you can write the KCL as rule as I1 plus I2 plus I3 equal to 0. Since there is no other current sources, you can write it, you can equate it to 0. So you can write the equation for I1. What is I1? I1 is the current flowing through the branch containing the impedance Z1. So I1 can be written as VA minus V1 divided by Z1. What is I2? I2 is equal to VA by Z2. What is I3? I3 equal to VA minus VB by Z3. So first equation can be written as VA minus V1 by Z1 plus VA by Z2 plus VA minus VB by Z3 equal to 0. That is first equation. You can rearrange the equation by taking VA outside. So you will get VA into 1 by Z1 plus 1 by Z2 plus 1 by Z3 minus VB by Z3 equal to V1 by Z1. That is first equation. So this is by considering, this is the equation that we got by considering the node A. Next we will consider the node B, and you have to mark the voltage, node voltage as VB, and you have to then mark the branch currents, that is all branch currents are leaving the node B, and you can apply the Kirchhoff's current law such that it will give I3 plus I4 plus I5 equal to 0. Here there are no current sources, so you can equate it to 0, that is I3 plus I4 plus I5 equal to 0. Similarly, you can write the equation for I3 as VB minus VA by Z3, I4 will be equal to VB by Z4, I5 will be equal to VB by Z5 plus Z6, because in that branch Z5 and Z6 are connected in series, so the current through that branch will be equal to VB divided by Z5 plus Z6. So the Kirchhoff's current law can be written as VB minus VA by Z3 plus VB by Z4 plus VB by Z6 plus Z5 equal to 0. And you can separate VA terms and VB terms. So you got the equation minus VA by Z3 plus VB into 1 by Z3 plus 1 by Z4 plus 1 by Z5 plus Z6 equal to 0. That is second equation. So you got two equations, equation 1 and equation 2. Both are in the variables VA and VB. So you can solve those equations 1 and 2 in order to get the unknown variables. So this is the method how we can solve the equations using nodal analysis, and here the primary concern is that here the input source is the AC source. Okay. So let us do a problem. In the network shown in the figure, determine VA and VB. The network contains 10 angle 0 degree, that is a voltage source, that is an AC source. It contains an inductance having value J6 ohm and capacitance having value minus J6 ohm, resistance 3 ohm, another inductance J4 ohm, another inductance J5 ohm, and another capacitance minus J4 ohm. This is the circuit diagram, and here you are asked to find out VA and VB. So you can use nodal analysis in order to find out VA and VB. So first of all, you have to consider each and every node, and you have to mark the currents in every node, and you are assuming that all the branch currents are leaving that node. So starting from the node A where the voltage is VA, you can draw the diagram, and the branch elements connecting to the node A are inductance 6 ohm, capacitance minus 6J ohm, and resistance 3 ohm. So I1, I2 and I3 are marked, and then we can write the Kirchhoff's current law equations, that is I1 plus I2 plus I3 equal to 0. And here I1 equal to VA minus 10 angle 0 divided by J6 plus I2 equal to VA divided by minus J6 plus I3 equal to VA minus VB by 3. Here you have to consider, if you are considering inductance, its value will be J6. If you are considering capacitance, its value will be minus J6. So you have to incorporate positive and negative sign, also J there, okay? Because it is an AC circuit, so you have to consider the impedances. And next, we can rearrange this equation by taking VA and VB separately. So you will get VA terms are VA into 1 by 6J minus 1 by 6J plus 1 by 3 minus VB by 3 equal to 10 angle 0 by 6J. So this is obtained by separating VA and VB terms. So you can write this 1 by 6J minus 1 by 6J will be cancelled out. So VA by 3 will be there, minus VB by 3 is equal to 10 angle 0 divided by 6J. That is first equation. And next we will consider node B, and you can draw the node B diagram as at node B 3 ohm, 4J, 5J and minus 4J are connected, and also you can mark the currents as I3, I4 and I5, and all the currents are leaving the node. So you can write the KCL equation as I3 plus I4 plus I5 will be equal to 0, since there are no current sources. So you can equate it to 0, that is I3 plus I4 plus I5 equal to 0. Then you can write the equation for I3. I3 will be equal to VB minus VA by 3, that is from the diagram. Next I4 will be equal to VB divided by 4J. Next I5 will be equal to I5 will be equal to VB divided by 5J minus 4J. See here inductance 5J and capacitance are connected in series, and so its reactance can be written as 5J minus 4J, that is it can be summed, reactance values can be summed. So the equation will be VB minus VA by 3 plus VB by 4J plus VB by 5J minus 4J equal to 0. Then you can simplify it as VB minus VA by 3 plus VB by 4J plus VB by J equal to 0. And in this VA and VB can be separated, that is, so we will get minus VA by 3 plus VB into 1 by 3 plus 1 by 4J plus 1 by J equal to 0. So minus VA by 3 can be written as 0.33 VA minus 0.33 VA plus VB into 0.33 plus 0.25 J plus 1 by J can be written as here 1 by J equal to, if we are multiplying with J by J, you will get minus J. So 1 by J can be written as minus J. So you got the equation minus J equal to 0, that is second equation. So you have first equation as where is the first equation? You have the first equation as VA minus 3 minus VB by 3 equal to 10 angle 0 by 6J. And that the first equation can be rearranged as 0.33 VA minus 0.33 VB is equal to 10 angle 0 degree divided by 6J can be written as 1.67 angle minus 90 degree. See, this is equation. How you can write a 10 angle 0 divided by 6J like this? You can see 10 angle 0 can be written as 10 angle 0 itself, but 6J can be written as 6 angle 90 degree. That is a simple notation, that is 6J can be written as 6 angle 90 degree. So 10 divided by 6 will be taken, that is 1.66, and 0 degree divided by 90 degree in the polar form it will be subtracted, so you go to minus 90 degree. Okay, so you got first equation as 0.33 VA minus 0.33 VB equal to 1.67 angle minus 90 degree. See, you should know how to solve how to change the polar form into rectangular form and rectangular form into polar form, and those you should know. And then you should know also how can we divide a polar form from another polar form, those things you should know, and you should just recollect those things from your first year classes. Okay, and for the problem I have done the steps how to convert rectangular form into polar form. Here you can see 6J is converted into 6 angle 90 degree. Okay, so if we are dividing a polar form from another polar form, the angle terms will be subtracted and magnitude terms will be divided. So you got 1.67 angle minus 90 degree. So that is equation number 3. So we got equation number 2 and equation number 3. See, you can see that here equation number 2 and equation number 3, you can solve it as first term VA term will be cancelled out if we are adding 2 and 3. See, equation number 2 contains minus 0.33 VA and equation number 3 contains plus 0.33 VA. If we are adding equation number 2 and 3, that term will be cancelled out. So in the next step, equation 2 and 3 are added. So we got VB into VA terms will be cancelled out. So we got equation VB into minus 0.25 J minus J equal to 1.67 angle minus 90 degree. So that will be equal to VB into minus 1.25 J equal to 1.67 angle minus 90 degree. So VB will be equal to, we can write it as 1.67 angle minus 90 degree divided by minus 1.25 angle 90 degree. So 1.67 divided by 1.25 will be equal to minus 1.34, and minus 90 degree and 90 degree will be subtracted. So you got minus 180 degree. So the steps of reduction is shown in the shown as rough work. That is 1.67 is divided into 1.67 divided by minus 1.25 is equal to minus 1.34, and minus 90 degree minus 90 degree equal to minus 180 degree. So we got a VB value. So in order to find out the value of VA, we can substitute the VB value in any one of the equation. Here I am substituting the VB value in equation number 3. So I got 0.33 VA minus 0.33 instead of VB I am writing minus 1.34 angle minus 180 degree. So VA can be written as VA equal to 1.67 angle minus 90 by 0.33 minus 1.34 angle minus 180. Here I am dividing every term with 0.33 and I am rearranging the equation in order to get VA. So VA will be equal to minus 1.67 J divided by 0.33 minus 1.31. See, 1.31 angle minus 180 degree will be equal to 1.31. So you know that a polar form can be changed into a rectangular form like this. Here, if R angle theta is a polar form, then it is converted into rectangular form in this manner. That is R into cos theta plus J sin theta. Okay, that is the thing. So R angle theta can be converted into rectangular form like that, R into cos theta plus J sin theta. Similarly, I am using that thing here. That is 1.31 angle minus 180 degree will be equal to 1.31 into cos minus 180 degree plus J sin minus 180 degree. But that term will be equal to 1. So I got 1.31 alone. So similarly 1.67 angle minus 90 degree will be equal to minus 1.67 J. So I can do VA equal to minus 1.67 J divided by 0.33 minus 1.31. So VA will be equal to minus 5.061 J minus 1.31. And I am changing the polar notation to rectangular notation in order to solve the equation. And based on the need, you can change the rectangular form into polar form or polar form into rectangular form. That depends upon the nature of the problem. Okay. So finally we got VA will be equal to minus 1.31 minus 5.061 J, and it again converted into polar notation as 5.22 angle minus 104.5 degree. And you can use calculator in order to convert the rectangular form into polar form or polar form into rectangular form. Calculators will help you. And here I am using the simple mathematical procedure to convert a polar form into rectangular form and a rectangular form into polar form. And here the rectangular form is minus 1.31 minus 5.061 J, and it is a rectangular form, and it can be converted into polar form like 5.22 angle minus 104.5 degree. How can we convert that? The magnitude term will be obtained by the method square root of 1.31 square plus 5.061 square. That will give the magnitude term as 5.22. And angle term will be obtained by angle will be equal to theta into minus of 5.061 divided by tan inverse of 5.061 minus 5.061 divided by minus 1.31. So we will get the angle as minus 104.5 degree. Any method you can use for saving the time. You can use the calculators and you can simply do the problem. Okay. So there is no difficulty in doing this problem because the procedures are same. Only the difference is that here we are using as AC sources. So we have to consider the impedance term, and so it will be in the polar representation or rectangular form. So you have to do calculation on that polar form or rectangular form. That's the only thing. Next we will go to the second module. Bye.